this better? This is better. What happened to your phone?
Oh, I don't have it.
Oh, there you go.
Thanks everybody for coming, and thanks to the organizers for inviting me and putting up with me for a few days. So this is a status update on lattice assumptions for cryptography, and I'll cover some work with Oded and Noah. So yeah, as you've all said before lunch, the 20th century has been very good for crypto, and we do a lot of great stuff with exponentiation and factoring and linear pairings. That is still, linear pairings still count as 20th century because Zhu found it, I think, in 2000, right? So very, very good century for crypto that allows. Yes.
I cannot hear you well.
You can't hear me well. Can everyone else hear me well? You might just be in a dead zone. Dead zone
No, you just speak up.
Okay, I'll speak up. I'll also turn this up.
Is it on?
Mic is on. How about now? Better? No better. Worse.
It was identical.
Now? No better?
Just speak up.
I'll just yell the whole time.
I think the microphone at the podium also has more pickup to it. Maybe that could help. I don't know.
How about now? Test, test, testing. Okay. So I'll either manually increase my volume or sound through. Okay, so 20th century, and the idea with lattices is let's see what we can do with very different problems on lattices instead, using problems like finding short vectors in lattices or detecting whether short vectors exist in high-dimensional lattices. I could only draw two-dimensional lattice here, but I think hundreds or thousands of dimensions. So why should we want to do this? Well, we've had a lot of success in the 21st century with this approach. We can get crypto systems which are very efficient. They have very parallel and linear operations, which is nice. So far, they've been able to resist quantum attacks, which is also nice. We get security from worst-case assumptions, which we'll be talking about a little more in this talk. And then we get these great solutions to holy grail problems like Yuval's slide shows up HE exploding out into this great 21st century. So some people draw gardens and Yuval draws bombs. I don't know. What is he? So anyway, that's what the landscape looks like. So I won't be talking too much about applications at all, really, in this talk, because the workshop is about assumptions. So we'll be talking about the problems, the lattice problems and assumptions that have enabled all this fun stuff. Okay. And I won't just be talking about assumptions, I'll be talking about the assumption. Okay, the assumption that has been so helpful to us is Oded's learning with errors problem from 2005. So probably many of you know learning with errors, many of you may not. So I'll introduce it, and there are three main parameters. There's a dimension, which I'll call n, a modulus q, and an error rate alpha. And when you write LW papers, you should use these symbols as well. So what's the problem? Well, it comes in two flavors that will be relevant for this talk. The search flavor is we have a secret vector S, which is chosen randomly as an n-dimensional vector with entries modulo q. And you should think of q as being pretty small, like a small polynomial in n, maybe n cubed or something like this. So q is pretty small. It's not 2, but it's not much bigger than 2. So we have a secret vector S. And the problem in the search version is we want to find the secret given many random noisy inner products. So we get samples. We get to press a button and we get back a sample. A sample consists of a random vector A, dimension n, not q again, and then the inner product of A and S, but with some error added into it. And then we can press the button again, and we get another sample, and we can have as many of these samples as we want. So if there were no error in this picture, then it would be very easy to solve for S just using linear algebra. You use Gaussian elimination. You get enough samples so that S was uniquely determined, and then you would solve for S. But the error here is what's going to make this problem harder and more interesting. So to be more precise, what's the error? Well, we take the inner product and then we add an independent error term, E, where the error is, canonically, it's shaped like a Gaussian. So we have a Gaussian here, and the width or the standard deviation of this Gaussian is like alpha times q. So alpha being the error rate, this is like the relative amount of error there is with respect to the entire cycle of values mod q. So we have width that's basically size. The size of the error of this distribution is alpha times q, where alpha is the error. All right, and so because of this error, this problem seems to be very hard. It seems to be hard to find the secret. There's the other variant of the problem, which is a distinguishing problem, which syntactically appears to be easier, which is just to distinguish one case from another. In one case, you're given samples which are generated in this fashion, and then in the other case, the samples are generated uniformly at random. There's no secret, there's no error. The VIs are just random and independent from uniformly independent. Okay, and the goal here is to just tell, are my samples of this form or of that form? So LW is great. It's very hard, and it's also very versatile. And we have a next sequence of reductions starting from 05. So I will go from the right to the left here. There are now probably 100 or more papers that build cool cryptography, assuming that the decision LWE problem is hard. So it's assuming the pseudo-randomness of LWE samples, you can build a lot of nice crypto, including FHE and all this other good stuff. Moreover, we can show that the decision problem is at least as hard as the search problem. So even though decision seems like an easier task, it's not, because if you can solve decision, then you can solve search. And this actually goes back to the 20th century, so this is Blum versus Princeton Lipton, I think, yeah, from 93, and a generalization of that to go good, 2005. And then the really interesting side of this is that if you can solve the search problem, then you can solve these worst case problems, like worst case short independent vectors problem on any n-dimensional levels. Okay, so being able to solve search on the average is an average case problem. There's a lot of randomness involved in the instances. Being able to solve search allows you to actually solve any lattice in this worst case SIVP problem. And this is an approximation factor here. So you can solve it to within an n over alpha factor. So the approximation factor decays inversely with the error rate. The smaller the error rate, the narrower the error, the weaker of an approximation you get here. But it kind of scales nicely. Yes?
Can you say something about how the hardness of all these questions changes with the size of Q? Like if Q is equal to or if Q is exponential?
Right, okay. So if Q equals 2, then there are kind of no interesting error rates to speak of, or the error rate has to be very slow.
Isn't that LPN?
Yeah, sorry. Okay. What I've hidden here is that the alpha Q width has to be at least square root n or so. Okay. So if Q is 2, that means alpha is like square root n. And when the error rate is larger than 1 or appreciably larger than 1, these samples are just uniform anyway. So there's no, the error rate is so large that the error swamps
So
out.
I'm wrong in thinking that learning parity with noise is basically like LWE, but with Q equal 2?
Q equal 2, but with an error rate that is very small, like
right.
1 over n or something like this, right? And it fails to satisfy the conditions needed for this reduction.
And what if Q is really big?
If Q is really big, then we can say a lot of things. all this applies here.
But is it hard? The problem is hard?
Yeah, it's hard. I'll talk about the parameters in the next slide as well. Yes, what we here. Okay, so what this says is if you could solve search LWE, then you can solve these worst case problems on lattices. This is interestingly via quantum reduction. So what it says is if your search solver is classical, your SIDP reduction, your SIDP algorithm will be quantum. And like I said, as far as we know, none of these problems are solvable by quantum computers. So this is a meaningful reduction. And then if you're concerned about quantum, you can get a classical reduction from a somewhat different problem, still seemingly hard, with appreciably worse parameters there. So you don't have to have quantum here, but it sure helps. Okay, so this is the kind of chain of things qualitatively, but let's talk about the hardness, the actual parameters, and what we can say about hardness. So again, we have the parameter, the dimension is n, modulus is q, the error rate is alpha. So the reduction that was on the leftmost side here, from lattice problems to search LWE, is really nice. There's basically one reduction that gets the best known parameters in all fashions. And all you need is for Q, the modulus, to be at least root n over 1. Okay, so this rules out the LPN case when Q is 2, simply because if Q is 2 here, then you need alpha to be like also 2 root n, and that's just so much noise that it just blasts everything away. Everything is just uniform. So it's kind of the problem is trivially hard, but also useless. But as long as, once you allow Q to be bigger than root n, maybe n or so, this starts to make sense, and you can use it as well as get a hardness result. So that's the lattices to search reduction, and then the next step of the reduction was from search to decision, relating those two. Here, the state of the art is somewhat more messy. There are many incomparable reductions, which are quite sensitive to the form and size of Q. So there'll be a quiz at the end, so remember all of these, if you can. It starts out with any prime Q that's polynomially bounded. Then you can get this reduction. Then this is generalized to a somewhat smooth Q, so a product of many distinct primes that are neither too large nor too small. That's one generalization. Another is any Q that's a prime power. Okay, if the prime still has to be large enough, but not too large. Just right. There's an interesting case here of any Q that's a prime power, where now the prime does not have to be, now the prime could be small, it could be 2, for example, but it's uniform error modulo some other smaller power of the prime. So that's a little weird. So far, I've only considered Gaussian error, which is what you need for this upper reduction here. So this is a little bit of an outlier, but it does say something about search versus decision. The next one is, hey, any Q that's the power of a prime could be 2, and it does apply for Gaussian error, but it increases the error rate. So you pay in the error as you have related search to decision. Not so great. And then lastly, you can get any modulus you want via something called modulus switching, but the error rate then can increase quite appreciably from that. So, you can get basically any modulus for decision to be hard for any modulus, but you kind of have to figure out how much do I have to pay in my error rate to get this, which reduction applies, which is the best one for my situation. It's not such a great situation. Yes.
Which one of those primes, if I want to, like, say, set exponential modulus to my solution,
Right.
what are the primes that are?
Which ones work?
What are the
Right.
modulus that work?
Yeah, so if you're doing like FHE or ADE or something where you want a noise, an error rate, which is like 1 over n to the log squared n or something like this, you'd have to find which one of these applies. This one won't, right? But this one kind of gets worse. You can generalize to this being quasi-polynomial or something. The runtime of the reduction gets worse. So that's the question, right? Like, which one? What do I do if I'm in that situation? You have to call somebody to figure it out. I mean, that's the point. It's messy, right? The situation is not so.
And you would not suggest to use a modulus word decision to search with more force.
It leaves you open to some kind of risk, I guess, or uncertainty about whether this is safe to do or not. Okay, that's also, yeah, there are definite, one example would be like a huge prime. Which ones apply here? Well, this one will always apply, but you'll pay for it in your error rate to some degree, and so your assumption is hard to nail down. What exactly is it? Yes.
So just following on that comment about risk. So are there values of Q where decision seems to be easy, but
Right. Great question. So do we know of any examples where search is clearly covered, but decision for some strange reason is faulty and we know how to attack it? No. Okay, we don't have any such really natural pathological examples. Right. So the current situation with search versus decision is quite unsatisfactory in this respect, because we don't even know what not to do, if anything.
Are there situations where you wouldn't just go with the first option and pick a prime Q that's polyadic?
Yes, so Rachel's example is one where there are applications where you need to use a sub 1 over super polynomial error rate, and then the first example will not work. So, foreshadowing here, we're going to take care of this. So, as I mentioned, auditing is pretty efficient. We get one pseudo-random scalar, we get one B CQ that's pseudo-random at the price basically of one inner product, and one n-dimensional inner product here. Mod Q. And you can do even better, you can amortize each single A vector over many secrets, but you still have to do a linear amount of work to get each scalar out there. So not terrible, but maybe not the best for it. Also, this kind of enforces that cryptosystems have to have pretty large keys. So a typical cryptosystem, the public key will be some matrix A that's made up of rows like this. These rows here, and you need at least n rows, or maybe n log q rows to do what you want to do. And so the public key is quadratic in the dimension, and the ciphertexts are at least linear in the dimension. So rather large keys. So here's some wishful thinking that you might have. If you're being very greedy, could we get maybe not just one, but n pseudo-random scalars from just one cheap product operation? Okay, so could there be an operation where I take A times S, and it's not an inner product, it's some kind of other star product or something, that returns a vector, still returns a vector, and then I add a vector of noise, and I would get a vector of these. So could there be a cheap operation that allows me to get this and still have security or still targets? And so the question is, how could you hope to define this star operation so that these A, B pairs, where now the B is not just a scalar, it's a vector, n-dimensional vector still, so that these pairs are still pseudo-random decisions. If you're really careful about this, if you do the most naive thing, of just doing, say, coordinate-wise multiplication up here, and if your errors are small, then this is completely insecure. You can break it. I'll leave it as an exercise to do, but it's not too hard to show how to break this. So you can't. There are some choices here which are just clearly insecure. The question is, are there any that are secure? And the answer is yes. If we define multiplication to be, or the star operation to correspond to multiplication in a suitable polynomial ring. So the idea here is we're going to let the A vector and the S vector correspond to elements of a polynomial ring, think of them as polynomials, and then there will be polynomial multiplication that we do. And polynomial multiplication will be modulo appropriate polynomial here, and so you'll get an n degree, like a degree less than n polynomial back, to which you can add error and get a B vector. And this can be made even very fast and practical using FFT-like operations. So you can still do this product in quasi-linear time. Okay, so this is not actually like a new idea. In fact, it is a 20th century idea. Okay, so the 20th century does pop up here. This is kind of the ring structure that we used in the intro crypto system of 98, and then in more theoretical works from the early 21st century. So what we want to do now is to actually define this version of LWE here where we use rings more precisely and see what we can say about it. Say about starting. Okay, so LWE should go ahead. Oh. Thank you, I appreciate it. Please clap. So learning that there was over rings, ring LWE. Okay, so we have parameters. Instead of the dimension n, we now have a ring, which the ring has a dimension to it, n. But the ring will be the ring of polynomials, integer polynomials, modulo some specific irreducible polynomial f of degree n. Okay. Everything today will have this form. More generally, you can have the ring be the ring of integers of a number field. If you know what that is, great. If not, don't worry about it. Okay, so all the multiplications that we do, you multiply the two polynomials and then you reduce modulo f, some special f. Okay, now there's an important object called a dual ideal. This is called RV. So this is a special ideal which is kind of uniquely associated with the Joseph ring, and it comes from the canonical geometry of the ring. There's no north, but there's a special ideal that's important with the definition of the problem. As before, we have an integer modulus, Q. So Q will define this R sub Q. And this is just a quotient ring where we do R modulo Q. So all the coefficients now, all the integer coefficients are modulo Q. And then RV mod Q is similar. It's just the quotient group RV modulo Q times RV. Okay, so all the coefficients that are not equal. And finally, we have a Gaussian error as well, and there's an error parameter alpha. That's, again, the error rate. So the search problem here for ring LWE is we now have a secret, okay, but it's not a vector, maybe not best viewed as a vector, it's viewed as a ring element. And this is this S. It lives in the dual ideal modulo Q. And your goal is to find S given these noisy ring products. So not noisy inner products, but noisy ring products. So A is chosen from the ring modulo Q at random, uniformly. And then we give you B, which is A times S, that's a ring product. And so A, because RV is a ideal, A times S is also in RV. A is in the ring, S is in the ideal RV, so A times S is in the ideal RV, and everything is mod Q. Yeah. So S is not in S is in the ideal RV. Okay, and A is in the ring. So when you multiply an element of a ring times an element of an ideal, you get an element in the ideal. So we take A times S, that gives us an element in the ideal RV, and then we add error from the appropriate distribution. Okay, pictorially it looks something like this. The lattice here, you can view the ideal as a lattice. It's like these lattice points here, these dots. And then the error distribution would look like this kind of blurry red Gaussian thing here. So you would choose, and the width of the Gaussian is like alpha q. So you would choose an element from this distribution and add it to the product of A times I. So everything is a ring product, and we're doing a ring addition. Add. Any questions so far? Different. Yeah.
And F only needs to be irreducible over the integers.
Over the integers. That's right.
Doesn't need to be irreducible over
Right.
inverse mod
In fact,
Q.
yeah. So in fact, F may not be irreducible modulo Q, but it's irreducible over the integers. That's so that we have a legitimate ring of integers in the number. So. Yes.
Just really simply to clarify, is E a value or E sampled within a range?
Right, so E is drawn from a distribution, like this distribution of the kind of red blur here, right? So it's centered around 0.
You just said it's simply when you're saying plus. So why is it an error rather than an offset?
It's an offset. Yeah, you can see it as an offset. We just like to call it an error term because we're kind of blurring the product A times S and messing it up a little bit. Is there another question? So just as an exercise, if we were not adding these errors, this again would be easy to solve. You would be able to solve for S. Basically, one sample is enough, one pair. You would just find A inverse and multiply A inverse times B, and that would wipe this out, and you'd be left with this. So A would have to be invertible modulo Q. That happens pretty often, most of the time, and so you win just by doing that. But with the error in here, that attack is now foiled. You have to do something much harder, much more sophisticated.
And if you choose S from the full ring, like this, it doesn't make sense. Why should I have chosen from this idea?
From the special ideal? Yeah, so it comes out in the hardness proof of why it's important. And it actually comes out also in the attacks as well. This is sort of the most natural thing, both for the hardness proofs and for the applications. Well, what matters the most is, are we working in RV or are we working in R, and how does the error distribution look compared to the lattice that we're using? So you can transform this to work entirely over R if you kind of also transform the error distribution in an appropriate way. You can do it in like a lossless fashion. What's important is how does the error look relative to the ideal that you're using or not.
You're saying they're the same, right?
Here I'm saying that the most natural thing to do, it turns out, both for the proofs and for applications, is to use RV and to use a kind of basically a spherical Gaussian error. These are the two things that work together.
So the error is the idea.
Yes, yeah, the error would be over the ideal. I've drawn it continuously here, but you would kind of round it off to the ideal. Yeah, so the one property that's very handy is that if you add a spherical error to the ideal, you can decode it well. So when the person who knows the secret key will be able to remove the A times S part, and will be left with the error. And this error is very nicely decodable on this special ideal. You have to remove the error eventually, and it's very nice to be able to do that with this special ideal. And then it also comes up very naturally in proofs, which I can assert that, but you can't see that right now. Any other questions about the definition here? Okay, so we just had the search algorithm, search problem, which is to find the secret. The decision problem, as you might expect, is to just distinguish samples having this form from samples that are completely uniform in independence. And have no secret, no error, no nothing. Okay. So, as before, with plain LWE, In the ring setting, we also have reductions, which look in many ways similar to what we had before, but also have some important differences. So starting from the left, what we have is we can reduce worst case lattice problems like approximate SIVP to the search ring LWE problem. With one important difference, the lattices are special. So these are worst case lattices, but they're ideal lattices. So these are lattices that correspond to ideals in the ring R that we've chosen. So this says that if you can solve search ring LWE, you can solve approximate SIVP on any ideal lattice in the ring. And I'll say in a moment what those look like. And this reduction is quantum. It applies to any natural ring that you choose. And then there's also a search to decision reduction here. But this one is much more restricted. It only applies to what are known as Galois rings, which are relatively rare. They have a lot of, what makes a ring Galois is that it has a full complement of automorphisms. There are not too many classes of such rings that we have. Okay, so just a word on ideal lattices. Here's an example. In yellow, we have the ring ZX mod 1 plus x plus x squared. This is actually the third cyclotomic ring. And in blue, we have the ideal, which is generated by the element 3 and 1 minus x. So it turns out this is an ideal, and it's the points in blue. That's a subset of the ring, which is closed under multiplication by the ring. So if you take any element, any blue element here, and multiply it by any yellow element, you will get a blue element. And there's a huge number of ideals in this ring or in other rings. And what this reduction tells you is you can find short vectors in any ideal lattice of the ring, assuming you know how to solve search. Yeah.
So you're going to tell me which one you know about the hardness when you compare it to
Yeah.
LWE?
Yeah, I'll get the
There's so many parameters, right?
Yeah, many factors. So we'll say what we know about the hardness of this problem. Okay, what I want to highlight here is there's a large disparity in what we can prove about search versus decision for ring algebra. So again, the reduction from worst case problems to search applies really to any number ring that you like and any modulus Q that's big enough. Basically, some small polynomial on n divided by alpha. And that's a very close analogy to what we know about the search plane element development as well. But with decision, we have to choose a Galois ring, for example, cyclotomic ring, and we also need to use a prime Q, which is polynomial in n, and it has to split highly in the ring. So it's kind of a special number theoretic condition on Q ring. Now you can turn this into any Q by using some modulus switching, which I mentioned, this big hammer, but that increases the error rate, so it's somewhat unsatisfactory. So the real restriction here that's troublesome is that we have to restrict to Galois number rings in order for this proof that we have here to go through. So bottom line, we have no known hardness for decision in non-Galois rings. But anticipating Salil's question again, we also have no counterexamples. So we have no examples where decision is easy or substantially easier, where search is still worst case hard. And you can rule out a lot of natural classes of attacks, but you certainly, we didn't really have any counterexamples. So the natural question is, is this restriction to Galois really essential, or are we just missing something in our purpose? So now we can say something a lot better, which is the new results with the data known, which is that, in fact, ring LWE, the decision version, is hard for any choice of ring. Pseudoring of anything. So what we're able to show is that we can give a direct reduction from the worst case lattice problems to the decision ring algorithm. Instead of going in 2 steps from search and then to decision, we're going to go directly to decision. And this proof is going to be working for any number ring and really any modulus that's big enough relative to that area. Okay, so worst case SIVP, same worst case problem as before, directly to decision. And then we get a bonus out of this. The technique that allows us to prove this is also good for wiping out that big mess of search versus decision reductions for plain LWE. So for plain LWE, we also get pseudorandomness for any modulus. Again, going directly from SIVP, approximate SIVP to decision, and this works for any modulus that's big, regardless of the number theoretic form or size or anything of that nature. So both of these theorems actually match or mostly improve upon the previous best parameters. So whether you are not using rings or you do have rings, there's one reduction to rule them all. And it also seems to adapt to these modular lattices and this problem called modular LWE, which basically interpolates between plain LWE and ring LWE. It kind of gets you a smooth transition from the less efficient LWE to the more efficient extreme end of ring. We're not claiming that we proved this, but it looks like all of these things just kind of fall into place there.
Then you have over ideal lattices over the module?
What you have is you have SIVP on module lattices of a certain rank in a ring. Reduce module lattices are the worst case lattices, and then you'd be going to module LWE of the same rank. Or your choice of rank. Okay, so then the question, Stefano asked us, well, which rings should we use? One thing is our results don't really give you any guidance on what ring you should use. So they work within a single ring. You fix the ring, and then it says, well, ring LWE for that ring is at least as hard as ideal SPP on ideals in that ring. So, and unfortunately, we don't really have any non-trivial relationships between these lattice problems in different rings. Apart from some simple, like one ring is a subring of another, pending conclusions. Yes.
Is there any relation between looking for relations between lattices and looking for relations between discrete log modules, different primes?
Yeah, you could definitely say that there's some kind of analogy there, right? Discrete log in one
There's
group.
no formal relations that are known.
Right.
You can show something in the lattice realm, it will translate to showing relations between. Suppose you did have anything
right.
Trivial, would you imply anything about discrete log?
That's also a good question. I have no idea. I mean, we really don't have any relations between lattice problems and discrete log. It's hard to tell, so it would be kind of surprising to see that happen, but that's a good question.
Yes, there's more simplistic question on the previous slide with the parameter C.
Yes.
It seems like things only get worse as C gets bigger, so.
C is a universal constant.
It's not. This is not for every C. This is for a particular C.
Right. Yeah.
Thanks.
Sorry about that. C is a universal constant. It was 1/2 in the plain LWE case. It's like,
or 1.
Or maybe it was. Yes, it was 1. Thank you. It was 1. It's like 1 plus 1/4 or something.
I see. Okay.
Big constant. It's a small constant. Okay, so we can't really compare different rings in any way. This is a really nice question. There has been some recent progress, so this is a status update. There's been some recent progress on this ideal SIVP problem. What we have here in a sequence of works is, so what we have is quantum polynomial time SIVP algorithm where the approximation factor is basically 2 to the square root of n. And that's for prime power cyclotomics. There's some heuristics to make that work, but this is basically the bottom line. You get 2 to the square root n approximation in quantum polynomial. So that's a pretty large approximation. It's large. It's much smaller than what we can do on general lattices quantumly, but it's also much larger than the assumption you need to usually make when you're talking.
If that's for all light?
This is for all ideals. Yeah, this is worst case. Yeah, worst case ideal SIVP in these rings.
Not just principle.
Not just principle, right? Yeah, the latest the CW Kramer, Dukan, Misalowski went to arbitrary ideals. So yeah, like I said, this is far from the polynomial factors or quasi-poly factors that matter for crypto, but it's also a lot smaller than the exponential factors that we are kind of stuck at for general lattices. It's kind of an interesting situation. More interestingly, so far the attacks here, the algorithms for this problem, don't seem to be applicable to ring LWE itself or even the entry itself. So they really depend on the ideal structure of the lattice, and we don't really know how to cast these problems in terms of ideals themselves. That is, we have the ideal SVP is lower bounding ring LWE, but not the converse. We don't know if ring LWE can be solved using even a exact SIVP or ideal bounds. So this is an interesting open problem. I'll highlight again. So you have some options here. Say what do you worry, and just using ring LWE over cyclotomics, which is the most popular choice. You can use ring LWE over alternative, slightly slower rings, like something like this, or you can use this like higher rank problem, like modulo LWE over your choice of ring. And it seems like as the rank increases, the problem gets kind of more general and harder.
Is there even a
There's less structure.
Is there even a reduction from modulo LWE to ring LWE?
Yes, but from ring LWE to modulo LWE.
Yeah, sorry, yeah.
That's easy to see just kind of by padding.
Yeah.
Yes.
So is the point or the reason there's kind of not a reduction in the other direction is that ring LWE works with a particular ideal, and ideal SVP is kind of all ideals, or?
No, what I would say is the most natural way of viewing ring LWE is you take these A's and they define a module over the ring, and then the B is like a BDD instance over that module. So it's a point in that module plus some parameters. And so this module actually has rank 3 or 4 over the ring. It's not an ideal in the ring. An ideal over the ring would be only rank 1 module. But the most natural, obvious way of looking at the ring LWE instance is a rank 3, rank 4, maybe higher module over the ring. And now you've lost the ideal structure. You still have the module structure, but not the ideal structure. You come to this random rank 4 module, and you have a point which is near it, and you have to decode it. And so that's what the main obstruction is in looking at this as an ideal nice module.
It's also a difference that FWE is more like PDD, like decoding nearby.
Yeah, so also the decoding part.
That's something they can do in this approximation factor.
Well, if you allow quantum, then you can say, let's just find short vectors in the dual and use that to solve PDD. So I don't know that that's the main obstruction. It's more that it's a higher rank module. I think it's the main difficulty that at least these authors seem to think is what's hard, or what makes this more challenging.
Yes. What would you get with LLL for that?
Yes, what you would get with LLL is something like 2 to the n here. Yeah, and so we're getting 2 to the root n, which is appreciably better. So, other questions here? there is. So LOL, the class of LOL and BKZ type algorithms gives you a trade-off between the approximation factor and the running time. What makes this interesting is this is a polynomial time, it's quantum, but let's put that aside. The polynomial time, they're giving you a much better approximation factor for free. As far as I know, there's no further trade-off from here to here. This is sort of just a special approximation factor where there is a natural barrier happening here. To get below it, you would have to use some very different technique to go below this. And so another problem is to try to get some trade-off from here in the polynomial time, some meaningful trade-off that is still better than BKC and all. Okay. So I wanted to give an idea of the new technique, and it's easiest to explain in the plain LWE setting. So remember, the theorem says that we have a quantum reduction from approximate SIBD to decision directly. And the reduction strategy, the kind of new idea, 50,000 feet, is we're going to play with the error rate of the LWE samples. Play with it, and we're going to use our oracle, we're going to use our distinguisher who can solve decision LWE. We'll use that distinguisher to detect when the error rate has decreased. So 50,000 with view thing. And when the error rate decreases, it kind of tells us some information which we can use then to eventually solve SID.
So you're skipping the search, you're doing the reduction directly?
Correct, yes. Yes, so to remind, we're going directly now from the worst case lattice problem to the decision problem, the problem of distinguishing LWE samples from uniform samples. So the idea again is, let's play with the error rate. So one quantity which would be helpful to define is, let's suppose we have some distinguisher, script O here. It's able to solve decision with for samples that have error rate alpha with some non-negligible advantage. So we're going to define the probability that this oracle accepts given samples that have varying error rates. So the beta, well, 2 to the beta, basically. So the error rate 2 to the beta will define P of beta. So the P of beta is your probability of accepting when your error rate is 2 to the beta. So this kind of log exponential thing will be convenient. So here's a nice plot that Noah drew. I don't know the function is here. It's just a squiggly. It's okay. So there's a potential.
Sign because
Yeah, okay. The combination of sign. There's a hypothetical oracle that we may have here, and we've plotted out the probability that it accepts as a function of the amount of error rate in the samples that you give it.
So you don't assume that it does better as the L.
Correct. Yeah, because it's an oracle. It's an adversary. Adversaries are jerks, and they sometimes, even when you give them less error, they say, "Hey, this looks uniform." It's a perfectly legitimate thing. Okay. So it can look like this crazy thing. But there are a few things we can say must be true about this function P of beta. So the first is that P of beta has to be pretty smooth or Lipschitz. It can't vary super quickly as you change beta. And this is because Gaussians of parameter sigma and tau are statistically pretty close. So if you change the width of the Gaussian a tiny, tiny bit, statistically you haven't changed much. So this function can't jump around too quickly as you vary the amount there. Okay, that's one observation. The second observation is that if you make the error rate large enough, so if beta is like log n or so, or larger, then P of beta becomes the constant function. It becomes the constant which is equal to the oracle's probability of accepting given uniform samples. Okay, so this is says that if you add enough error, eventually that error swamps everything out, and you really have uniform samples. So adding, so for beta greater than log n, p just flatlines somewhere. It could be at 0.7, it could be at 0.3, but it has a flat line somewhere, so we're showing that. And then the third observation is that because our oracle is a good distinguisher, the difference between p log alpha and p at infinity, or the flat line value, has to be noticeable. This just says that the distinguisher has some non-negligible range. So there has to be some noticeable change in p somewhere between log alpha and log n. It has to drop somewhere. We don't know. So the idea is to kind of find the place where it drops and use that using these observations. So now what we can do is talk about how we're going to reduce the lattice problem to decision. And we're going to recall the main, or one of the two main parts of DES 2005, which is the following. It says, if you give me an instance of BDD, this is bounded distance decoding. So you give me a lattice and a target T that is guaranteed to be within distance D of the lattice. So it's pretty close to the lattice. And then you also give me samples from this discrete Gaussian over the dual lattice, whatever that means. Just give me these samples along with the BDD target. You can produce LWE samples that have error rate alpha. Alpha is proportional to both D, the BDD distance, and R, the standard deviation of this Gaussian. So the error rate in these samples is the product, basically, of the distance here and the width of these samples. Now, where do these samples come from? They come from the previous iteration. It's the quantum part. They eventually get narrow enough that we can solve SIP. So I won't say anything about that quantum part, but all we need to focus on is this portion of the code. So our idea here is, again, the idea is to try to play with the error and see when we've made some improvement. So the idea is, let's take our initial target T, and let's just wiggle it a little bit, make a small change to it. And then use our distinguisher, let's use our oracle to check whether we've gotten closer to the lattice or not. Okay, and when we've gotten closer, we can say, hey, we're a little bit better, and then we can repeat. We can wiggle it a little more, so tell if we've gotten closer, wiggle a little more, and eventually we'll get close enough that we can just kind of round off and decode the lattice and stuff. So we make small, progressive improvements in how close we want. Or just use the oracle to check whether we've gotten closer. So let's see how to do this. We prepare the T to some T prime. We run the same procedure. We run it with samples. And the resulting samples will have error rate D prime now, the new distance times the same R divided by Q. And we invoke the oracle. And we'll actually invoke the oracle on many different values of R here. And ask and notice how often it accepts for each of these values. So what we're getting is basically, we can kind of, by doing this for both the original T and the new T, perturbed T prime, we basically get a suffix of the P function. Okay. Whatever original D was and the new D prime control where you start on this whole P function here. And
how do you know if you succeeded? The oracle is a distinguisher.
The oracle is a distinguisher.
Yes or no, and how do you know if it's wrong?
Correct. So we just run it many times and measure what was its acceptance probability.
Or just the probability that it says yes.
Yeah, the probability that it says
right.
yes. You just kind of run it many times, measure the probability that it says yes, and we're going to plot that. So the red would be the probability that it says yes for various values of R, and the green is the same thing here, same value of R. And what you get is just two different suffixes of P, and basically by kind of just matching up the red plot with the green plot, you can tell which one started farther to the left, and therefore which of T and T prime is closer. So that's, okay, we dropped from like 50,000 to maybe 25,000 T here. a lot more technical stuff to be done here, but this is kind of the main.
Maybe it's worth saying what happens when the adversary is not a jerk and it's actually monotonic CDP.
Oh, if the adversary is not a jerk, then it's much simpler. Yeah, you can just say, you just measure the adversary, and if it accepts more often on your new T prime, then you must have gotten closer.
And keep doing it.
And just keep doing that. Just take another step, tell you've gotten closer. Right? So we just use the adversary to tell us whether we've gotten closer by seeing, are we seeing more of the proportion than previously? So that's kind of the 25,000. Now, this is just for plain LWE. So just say a word or two about the ring setting. Yes?
So right now, the way dependent of the reduction of the number of samples.
No, right now we're just kind of assuming we have as many samples as we need.
For the use of those systems.
Yes. Yeah. Okay, so, yes.
If you choose a perturbation function, what's the probability that it gets you closer?
Okay, good. So it's good enough. You have to be careful about how large of a perturbation you choose, but in fact, you don't have to randomly perturb. You can just go up in the x direction, down, left, right, forward, back. One of these steps will get you like 1 minus 1 over n closer, and that's good enough to do this. So that's kind of a more classical trick that's been around for a while.
If you really move a little bit, it's half.
Yeah.
There you get closer, there you get further.
That's cheap. 1 out of 2 n directions. Okay, so just a few words about the ring setting, because the more interesting case here is with the ring, we don't need the Galois assumption, we still improve hardness of decision. So in the LWE proof, we have one parameter. The BDD distance corresponds to the error rate of your LWE samples. In the ring setting, there are n parameters. So there's a BDD offset vector, T, n-dimensional vector, and that induces an n-dimensional vector of error parameters, one for each dimension. And so there's Gaussian error of rate alpha I and of I dimension. So the classical part of the reduction basically says this offset E here, this BDD offset, together with these samples, gives you ring LWE samples where the error rate in the ith dimension is the product of the ith error term times the ith standard deviation of this distribution. And basically now the oracle's acceptance probability is not a one-dimensional function, it's an n-dimensional function from positive real, n positive reals to so one good thing is that if you crank up any single one of these error parameters high enough, you eventually get uniform samples. And this is non-obvious, but it happens to be true. There's a fortunate, lucky thing that happens there to make that true. And so we can crank up any one of these parameters to become very large, and that makes our ring LWE samples uniform. There's a technical problem, which is that our reduction never really produces spherical error, where all these alpha i's are equal to each other. And so it's kind of hard to force the oracle as a jerk, so it's hard to force it to give us anything. And so the solution to that is to kind of randomize these terms by adding a little more error in all directions. And then Adeb realized that there was a much smarter way to do this, which only increases the error by a tiny factor in each dimension, or else one on everything. You kind of do it in the worst case lattice world rather than to the error parameters themselves. Okay, so that's the setup improvement there. Okay, so I think I'm out of time. Wanted to leave with open problems. There are a lot of open problems. So like the point I just mentioned, hardness for spherical error, that it degrade by about n to the quarter, and it would be nice to avoid that. And also to support unbounded samples. So this alpha of the quarter actually, this end of the quarter actually hides a dependence on the number of samples that you're giving out. So to get rid of this would be very nice. Kind of a problem that tortures me is, can we get hardness with even smaller error but fewer samples? So we do some very limited results on this for plain LWE. This is motivated by practice. In practice, you'd like to have the smallest error that you can get away with for the cryptographic applications. And there's good reason to think that this still remains hard, very hard, if you don't give out many samples. But what exactly is the landscape there is completely unknown. As I mentioned before, can you relate any of these problems to each other across different rings? Seems really difficult, but maybe there's something to be done there. And then evidence for or against the converse reduction, right? Can you solve ring LWE if you have a perfect oracle for ideal lattice, short vectors and ideal lattices? We don't know. That would be really nice to know, for or against. And then the big question for all of this is to get classical reductions that match the parameters that we have for quantum reductions. You have to pay a lot for classical reductions when you even have them. Okay, that's all.
Time for one quick question.
So you say that even if you have like two different ways with different effects,
Right.
even if you move,
Yes. Yeah, you always know the FXs. Can you say anything about is one problem definitely safer than another? Is one ring better than another? Don't know. Yes.
You probably know in the real world now people are thinking of integrating
Right.
some of this stuff. And there is this claim that even though we don't have quantum computers now, if you need to keep something for
40 years.
yeah,
Yeah.
you should exist it already. So, what parameters these people should choose for thinking to be security 50 years? We're assuming that it will not be broken by quantum.
Assuming, okay, right. Assuming you won't get some kind of devastating quantum algorithm that will destroy everything. I mean, I think what the practical constructions so far, the practical implementations are doing is pretty good in terms of their approach. They really overestimate a lot of things. They use dimension n and like 1024 or a high, very close to 1,000, things like that. There seems to be a great deal of underestimation of the security for these. And still, the numbers that they get are very, very safe. And so the methodologies that are coming out from the New Hope and the Proto papers are being, I think, very conservative, and that seems to be the approach I would argue is the right one. In 40 years, our computers will be a lot faster too. So in 2 years, our computers will be much faster. So might as well be very conservative and use large parameters. Yes? Sure, yeah, that goes without saying. You use combinations. Right. So why would you? Well, I think these methodologies that they're using are already incorporating a pretty conservative view on what will happen, what might happen algorithmically, even with classical algorithms. You never know. You never know anything, right? Yeah, that's fair. I mean, I think all of these systems are combining like elliptic curve with lattice, and then with, to the XOR efficiencies that we have, things like that, which is obviously a good thing to do. There's no reason not to do that.
Any more questions? Please, again. We resume in half an hour. It's 4 p.m., so we still have time. 4 p.m.